In this video, we're going to cover section 7.2 on the hyperbola. This is our second conic section. A hyperbola is the set of points in a plane, the difference of whose distances from two fixed points, called the foci, is constant. So there are a lot of similarities between ellipses and hyperbolas, but the graphs look vastly different. All right, so a hyperbola has one of these two shapes. It has a center point, HK. It has foci, just like an ellipse, that move either left and right from the center or possibly up and down from the center. The definition says that if I were to locate my center and then use that to find my foci, if I were to put a point here on any point along either of these two pieces of the graph and find the distance from that point to each foci, the difference between those two numbers is always the same. Versus in a hyperbola, in an ellipse, it's the sum of those two numbers is always the same. All right, so hyperbolas consist of two branches that can open either vertically from each other like they do here. They open up and down. They look like two mirror imaging curves, similar to parabolas. Or they can open horizontally, left and right. All right, foci, just like in an ellipse, we have to locate our foci because they're part of the definition. Foci are always located C units from the center in whichever direction that the hyperbola opens. Okay, in other words, toward the vertices. These 2 points right here are called vertices, and over here, the vertices would be here and here. So if the vertices are located in a vertical distance from the center, our foci are going to move vertically to get to them. And if our vertices are located horizontally from the center, so are the foci. So it doesn't matter which way is longer this time. It matters the direction in which it opens, and we'll learn how to identify that in just a minute. This time, however, to calculate the distance to move to find your foci, the C is equal to the square root of a squared plus b squared. Remember, in an ellipse, it was subtraction of the denominators of our standard form. This time it's adding. So our standard form for the equation of a hyperbola, we have one for a horizontal and then a similar format for the vertical. So again, it looks a lot like an ellipse, except for instead of in between here where we were adding for an ellipse, in a hyperbola we'll be subtracting. So x minus h squared over a squared, just like the ellipse, but minus y minus k squared over b squared equals 1. So if the x squared term comes first, it's horizontal. So the x squared term has the positive coefficient. It's going to be opening horizontally like this one, left and right. When these two terms are switched around that subtraction sign and you have the y minus k squared over b squared being positive coefficient or coming first, minus the x minus h squared over a squared after the minus sign equals 1, so basically just switching the order of subtraction, that's when it becomes a vertical hyperbola, and it would open up like this. All right, notice up here in the diagram I drew in these dotted lines. It's kind of crisscross these dotted lines right here. Those are called asymptotes. So we will have to learn how to locate those and write their equations as well. All right, so our center is still HK. H is always inside with X, K is with Y. That doesn't change even if it's a vertical. H is always with the X variable, K is always inside the parentheses with the Y. So HK is always the center location. A, which is the square root of whatever's underneath the x squared. That's, again, the horizontal distance from the center to what we call the central rectangle. And we'll get to that part in a minute, what that looks like. B, the square root of whatever's under y squared, equals the vertical distance from the center to the central rectangle. Those dotted lines that we called asymptotes, these are lines through our center with slopes, plus and minus, because there's two of them, b over a. They represent the diagonals of what eventually is going to be our central rectangle. So if our asymptotes go through the center and have slope plus or minus b over a, the equation of the asymptote, y minus k, we're using point slope equation like we did back in chapter 2, y minus k equals plus or minus b over a, that's the m value, or values, times x minus h. I rewrote this with the k on the other side. I was looking at my math lab, however, after I made this handout, and you do not have to rewrite it. You can just leave it like this. You will have to put in two separate equations, one using the positive b over a here and the other one using the negative b over a, but you could just leave it just like this in point slope form. All right, so our first example, y squared over 16 minus x squared over 36 equals 1. All right, so the first thing I'm going to identify here is that since y squared has a positive coefficient, the y squared comes first. This is a vertical hyperbola. It's going to open in the y direction up and down. So our center, it's just x, so it's at h is 0, and it's just a y here, so k is 0, so 0, 0. A, we look underneath the x variable and take that square root, so 6. B, we look under the y variable and square root, so we get 4. So we got start at our center, 0, 0, left 6, right 6, plot 2 points, back to the center, up 4, down 4, plot 2 points. But this time through those 4 points, we draw this dotted boundary rectangle. That's called the central rectangle. That's going to help us sketch our graph. The vertices here, I don't think you have to state them necessarily, but you would know that they're the 0, 4 and 0, negative 4, these 2 points that are vertically located from the center because this was a vertical hyperbola. So those are going to represent a point that where the graph touches the central rectangle. Drawing in the diagonals of the central rectangle, those are my asymptotes. So we draw the central rectangle using our center and the A and the B. We draw in the diagonals for the asymptotes, and then we just fill in these branches either in these two regions that are located above and below, or if it was horizontal, then those branches would go side to side. Right, but because it was vertical, we put them up on top and then down here on the bottom. So that's the graph. These graphs are all multiple choice. You don't have to actually put together the hyperbola graph yourself in my math lab. You will have to state foci and asymptotes though, but otherwise you're just choosing the right picture. All right, to locate your foci, c equals the square root of, and we're just going to add the denominators, 16 and 36, so the square root of 52. We do need to simplify this radical, however. This is the same, this is 4 times 13, so we can reduce this to the square root of 4, which is 2, times the square root of 13. All right, so since my hyperbola was vertical, we move from the center in the vertical direction to get to the foci. So we add and subtract this number to the y value of the center. So that's going to give me 0, and then when I add 2 square root of 13 to 0, I get 2 times, for x, and 2 square root of 13 for y. And then if I subtract, I get 0 for x and negative 2 square root of 13 for y. Asymptotes, y minus 0, my center point k value is 0, equals plus or minus b over a, 4 over 6, times x minus 0. You don't really have to put minus 0 here, so this could just be y. You should simplify this to plus or minus 2/3, and then again you can drop the 0 here and just put the x. So y equals 2/3 x and y equals negative 2/3 x. All right, in our next example, they give us a graph, and they're just asking us to find the equation. We don't have to do anything else. Just write the equation if that were the graph. So we can see the central rectangle, we can see the asymptotes, and we can see the branches. So that should be all we need. Because these branches are located horizontally from the center, and it opens left and right, that's going to mean this is a horizontal hyperbola. So our center is located right here where the asymptotes meet at the origin, 0, 0. A is the horizontal distance, to the edge of the rectangle, so it looks like it goes right 3 and left 3, so A is 3. And then B is the vertical distance from the center to the rectangle, which would be 2, so B is 2. We just said it was horizontal because we can see it. So that means in our equation that the x squared coefficient, the horizontal direction is the x direction, has the positive, right? Or it comes first. So x minus h squared over a squared minus, because it's a hyperbola, y minus k squared over b squared equals 1. So this would just be x squared over 9 minus y squared over 4 equals 1. All right, our last example, similar to the last example from section 1, where we have to rearrange into standard form. All right, so similar steps we're going to take here. This one we would identify as a hyperbola before doing anything because we have an x squared term and we have a y squared term, but they have opposite signs. One's a positive coefficient and one's a negative. Anytime they have opposite signs, it's going to be a hyperbola. We can tell it's horizontal because x squared has the positive coefficient. But I still need to complete the square to put it in standard form. So we start by putting our positive term first, so 4x squared followed by the other term that involves x plus 8x minus 9y squared and the minus 18y, and then move the 6 to the other side, so this would equal 6. Within the x terms, we factor the coefficient out, so we take out the 4, leaving x squared plus 2x, and then we'll put plus blank. So we have a blank over here. Complete the square, so half of the 2, 1 squared, still 1, that's what we add inside. But again, like before, that 1 times the 4 on the outside is really a 4, so to balance it, we add a 4. With the y variables, we factor out the coefficient, negative 9. That leaves y squared. That changes this to plus 2y plus blank. So again, plus blank over here. Complete the square again. Half of 2 is 1. Squared is 1. That goes here. But when I multiply it by what I factored out, that is minus 9. So to balance it, we minus 9. So then we clean this up a little bit. 4 stays out here. This trinomial factors into x plus 1 squared minus, again, the 9 stays here. This, again, is the same thing, so it factors into y plus 1 squared. And over here, 6 plus 4 is 10, minus 9 is 1, so we get a 1. So this one is a little bit tricky just because we already have a 1 here, but we don't have denominators, we have numerators. Well, we need to make them denominators because that's what the standard form looks like, and there's nothing to divide by, so we have to move them to the denominator. So if I have to move 4 down to the bottom, it becomes 1/4, right? Dividing by a fourth is the same as multiplying by 4, so we can just do that same process backwards. So when I move it down, it becomes a fraction. It's like it's becoming a 4 to the negative 1 power, which is 1/4. Same thing with the 9. It moves down to the bottom, meaning it becomes a fraction, 1/9. So this is my standard form. Center, negative 1, negative 1. This is still a squared, so the square root of that would be a half, so a would be a half. This is still b squared, so the square root of that would be 1/3, so b would be 1/3. So we would move left 1, down 1, negative 1 for my center right here. Left a half, right a half to get to these two corners. And then from my center, up 1/3, down 1/3. So I have this tiny little rectangle drawn right here. Its diagonals are sketched to represent my asymptotes. And because it was a hyperbola where x squared had the positive coefficient, it's horizontal. So these 2 points right here would be my vertices, and I would sketch my curve in the horizontal sections determined by my asymptotes. To locate the foci, c equals the square root of, we add the denominators, 1/4 plus 1/9. So when I get a common denominator of 36, and this becomes then 9/36 plus 4/36, so 13/36. So that's the square root of 13/6. We can just square root the top, square root the bottom. So this is the distance I move horizontally from the center, because it's a horizontal hyperbola, to get to my foci. So I add and subtract this number to the x value of the center. -1 plus square root of 13/6, -1, and then -1 minus square root of 13/6, -1. And then finally our asymptotes, y minus -1, so y plus 1 equals plus or minus b over a, so 1/3 over 1/2, times x minus -1, or x plus 1. So this thing would simplify to 1/3 divided by 1/2. Remember, dividing by a half is like multiplying by 2. So 1/3 times 2 is 2/3. Again, I moved the -1 over and then just rewrote them as separate equations, but you don't have to move the 1 over. You could just write y plus 1 equals 2/3 x plus 1, and y plus 1 equals -2/3 x plus 1. It'll probably take this also, but you could have left it like this and just split it up into 2 separate equations. All right, so that is the end of section 7.2.